If you look at the top of your note page, today's notes are using similar triangles to prove proportions and also to prove that the products involving the line segments within the proportion are equal. So at the top of the page, it says to prove that the product of the lengths of two line segments is equal to the product of the lengths of two other line segments. The first thing we do is we form a proportion. And the proportion is based on the corresponding sides in the similar triangles. And then, again, you're proving that the product of the lengths of two line segments is equal to the product of the lengths of the other two line segments. So this is the cross product. And using the vocab, the wording goes like this. In a proportion, the product of the means is equal to the product of the extremes. So this may be familiar to you. I think it was back in middle school in which you were introduced to the vocabulary. In the proportion, the mean is here and the extremes is here. So here's the product of the means and here's the product of the extremes. So if you look at example 1, I have it all filled in, okay, in terms of proving the triangles similar, step number 5. So the method is the same from last class. We're just going to extend it now, okay, to prove that we do have a proportion, that AB to BC is equivalent to BC to BD, and that the cross product is the same. So we've already done part A, or it was done for you. So take a look at the example. I'm just going to highlight what has already been done within the proof. You were given that ACB is a right angle, and that CD is perpendicular to AB. That's step number 1. Down below in step number 3, given, again, the perpendicular segments, we have angle CDB is also a right angle. Step number 2 has angle B reflexive, congruent to itself, because we're looking at triangle ABC, which if I take the highlighter, is this larger triangle. And then we want to state, again, that it's similar to triangle CBD. So these triangles are overlapping, and they do overlap right at angle B, or they have angle B in common. So number 2, angle B is congruent to angle B by reflexive property. And again, given the right angles, all right angles are congruent. So here's the A for the postulate angle to prove two triangles similar. Now, in the triangles, I want to prove my next step. So given two similar triangles, we know from last class and from the reading that in two similar triangles, corresponding sides are congruent. So the next step in the proof would be AB to BC, which is what we wanted to show in part B, is equal to BC to BD. And my reason would just be that corresponding sides of similar triangles are in proportion. Some proofs will have you stop right here. That'll be the end. So in order to prove that corresponding sides are in proportion, you have to first prove the triangle is similar. Now the last part of the proof, which is to prove the cross product equal, we get BC times BC gives us the BC squared, instead of writing BC times BC. And that's equivalent to AB times BD. And the reason for that is, again, I just had a proportion, so I'm going to start and say in a proportion, I can't say the cross products are equal. I have to use the vocab. The product of the means is equal to the product of the extremes. And we're done. Now looking at number 2, got one more proof. This proof is proving that the product of the means is equal to the product of the extremes. So what I do before I start my proof is I break that up into the proportion. Again, it goes, we have DG times GF, so again, product of the means, DG times GF is equal to EG times GC. The other thing I do is highlight within my picture. So here's EG. I highlight DG. GF. So here's one of the triangles. I've highlighted two sides. Again, I'm looking at two sides of the similar triangle, which are proportion. So I'm going to connect these two sides to identify the triangle in which I'm showing the two sides proportional. So the last one was GC. So I'm trying to show, again, connecting with the third side. I want to show that these two triangles are similar. To prove similarity, again, the shortest way to do it is by angle. Angle. So let's look at the givens. We have DE parallel to AB. And we also have EF, I'm just going to extend it, parallel to AC. Now, looking at those two parallel segments, say with this transversal, I have these alternate interior angles congruent. So number 2, I'm going to say that angle 1 is congruent to angle 2. And I can start by saying that I have two parallel lines. I'm not trying to prove two lines parallel. So if two parallel lines are cut by a transversal, then alternate interior angles are congruent. But then also, in looking at this other transversal, okay, I have angle 3 congruent to angle 4 because these are also two alternate interior angles. So I'm going to add to that angle 3 congruent to angle 4 for the same reason. Now I could have also mentioned that these vertical angles are congruent, but I have enough right now with the angle-angle postulate to state that these two triangles are similar. So number 3, triangle blank is similar to triangle blank. Your similarity statement has to be in order of congruent angles. So if I start with G and I go G, C, D, I have to go in the same direction of angles of congruency. So angle 3 was congruent to angle 4. So I'm going to go G, F, E. And again, that is by angle, angle. Now after angle, angle, I've already proven the triangle is similar. Then comes my proportion. So this would be reason number 4, and this is going to be reason number 5. From the proportion, we can get the product of the means equals the product of the extremes. So I'm going to write those 2 steps, and then I'm going to write my reason. So it's EG over DG is equal to the length of GF to the length of GC. And that is because corresponding sides, same reasons as we wrote above, of similar triangles are in proportion. And then lastly, again, we have the cross products. So now, here's my statement I had to prove. DG times GF is equivalent to the length of EG times the length of GC. And again, I don't want to state the cross products are congruent. I want to state based on this statement above, which was proportion. In a proportion, the product of the means is equal to the product of the extremes. So again, we're just adding to that similarity proof we did last class. So from 2 triangles being similar, we can then prove that the ratio of 2 pairs of corresponding sides is equivalent, the proportion. And then from the proportion, we can prove that the cross products, again, worded appropriately, the products of the means is equal to the product of the extreme. On the back side, so pause if you still need to copy, otherwise you can move to the back side. We're going to prove, okay, given the altitude drawn to the hypotenuse of a right triangle. So what that means, again, if it is an altitude, we have a right angle here and a right angle there. So we know that CD is perpendicular to AB, given the altitude. Now, within that picture, we have 3 triangles. We have the largest one here, so I'll highlight that in orange. So I drew that first. Here's the largest one, and then they get smaller as you move to the right. Notice I put them all so that they are facing the same direction. Okay? So I have the longer leg to the short leg to the hypotenuse. The next largest triangle is this triangle right here. Okay? Again, rotated. Let's go and first put the first one, the right angle was at C. Again, the short leg being AC and the longer leg being AB. So in this case, right angle in this triangle is at D. My short leg is CD. My longer leg is DB in that picture. And then the hypotenuse is BC. And then with the smaller triangle, okay, we have the right angle at D. And then, again, the long leg is CD, short leg is AD. Again, LL, long leg, SL, short leg, H, hypotenuse. So when you have the altitude drawn within the hypotenuse, these 3 triangles are similar. So triangle ABC is similar to triangle CBD, which is similar to triangle ACD. So because they're all similar, I can go ahead and from there write my corresponding proportions. There are 3 proportions that we have in each. Again, I like to use the language short leg to long leg. So before I look at the examples, let's look at what we have in the picture. When we have given just the altitude and the hypotenuse, we have, again, the hypotenuse, when we draw the altitude, breaks it up into two segments. We can look at this as segment 1 and segment 2. Each of those segments is a long leg and short leg of one of those right triangles. Again, in a linear pair, if one of the angles is 90, its supplement is also 90. So if I compare, again, long leg to short leg of the one on the left, I have h over x. And then again, if I do long to short in the other one, it's going to be long to short, which is y over h. When I actually multiply h times h is h squared is equal to x times y. You can use the proportion or the equation, whatever you're comfortable with. So anytime you're given the altitude and hypotenuse, I tend to use the equation just because I know the altitude squared is equal to segment 1 times segment 2, but that's up to you. Now in the next one, we're looking at the bigger triangle in which we have the hypotenuse and short leg. So if I look at hypotenuse to short leg of that triangle, that's got to be equivalent to hypotenuse to short leg of the other one. So in this little one, the hypotenuse is a over short leg x. So again, when I do the cross product here, we've got a times a, which is a squared, equivalent to c times x. And then in the last picture, again, given the hypotenuse, this time we have hypotenuse to long leg. So hypotenuse to long leg of the bigger triangle, that is equivalent to the hypotenuse and long leg of one of the triangles within. So we have hypotenuse, because the right angle's here, hypotenuse b to long leg y. Cross product is b squared equals c times y. So again, I always look at the pictures in terms of long leg to short leg, or long leg to hypotenuse, short leg to hypotenuse. If you need to, you could also draw them separately as we did at the very top of the page. So given the three examples, they follow along with the proportion equation that's above it. So given the altitude and the hypotenuse, so these are the two segments that make up the hypotenuse, I again use the equation. So it's altitude squared equals segment 1 times segment 2. You can use the proportion, so or you can do long to short, which would be 6 over x equals long to short 9 over 6. You still end up with the 6 squared equal to 9 times x. So we divide, x is equal to, well first, let's square the 6, 36. Then divide by 9, and we get x equals 4. So in the next one, again, always look to see if they give you the biggest one. They do. I would check that first. We're given the 13, which is the hypotenuse, to the short leg A. So within the triangle, I want to keep the same ratio. And the other triangle that's given is this one. So then hypotenuse over short leg. And keep in mind that when you set these up, you should see within one of your cross products the same variable or something repeating. In this case, it's the a. Over here, it was the 6's. So it doesn't always have to be a variable. So a squared is equivalent to 52. To undo a square, I take the square root. So a is equal to the positive and negative of radical 4, radical 13. Reject the negative. And a is equivalent to square root of 4 is 2, radical 13. Last one. We're going to find the length of BC. So I'm going to call BC x. Now, I don't have the hypotenuse. I'm missing the hypotenuse. I'm also missing the other leg of the largest triangle. So I'm not looking at that triangle. I'm looking at the two triangles within. So within these triangles, if it's hard for you to know hypotenuse, oh, actually, I take that back. And looking at this triangle, I didn't have a leg or a hypotenuse either. So we are actually going to use I am given the hypotenuse of the larger one, and that's 10. All the way across is 10. So I'm given the hypotenuse of 10, say to the longer leg, x. And if you're always unsure which is the longer leg, short leg, bottom line is I have the hypotenuse in a leg. So the only other triangle I have a hypotenuse in leg to is this one right here. So hypotenuse is opposite the 90 is x over the other leg, 8. And again, you should always see that repetition with either your variable or one of the numbers. So now I have x squared equals 80. Taking the square root to solve for x, I get x is equivalent to the positive and negative. Again, rejecting the negative of radical 16 times radical 5. So therefore, rather than stating x, that was the length of BC. So BC is 4 radical 5. Again, you should always leave your answer in terms of the exact form. And the exact form means simplest fraction form or simplest radical form. And that is today's lesson.